Wishing you all are very healthy and happy. Let's begin with today's topic. As you know very well, we have just started the revision class of solution. And in our previous class, we have done what is Henry's law, what is Rolle's law. Moreover, we have done about the topic ideal as well as non-ideal solution. Clear? Now, in this same class, we are going to discuss the non-ideal solution, but with its two different types. That is non-ideal solution showing positive deviation and negative deviation. Clear? Moreover, I have told you that these non-ideal solutions showing positive and negative deviation, it is only dependent upon the molecular interaction. Okay, it's dependent upon the interaction, or we can say bonding between the molecules of the solute or solvent. Clear? Let's start with the topic non-ideal solution. First one, I'm talking about showing positive deviation. As I have told you that the non-ideal solutions are those solutions which do not obey the Rolle's law, Okay, that means they are showing the greater effect, or we can say they are showing the positive deviation than the non-ideal solution, so than the ideal solution. Yeah. Now let's discuss. See, if we have two molecules A, B, the two components A, B, we need to check out what is the bonding or what is the molecular interaction between these two components. So first of all, the compounds which are showing the positive deviation, they explains us that the molecular interaction level of the solvent, that is AB, is weaker than AA and BB. That means if there are two components present in the solution, a component is A, another component is B. And if we are checking out the molecular interaction level between the two, they are showing us that if A and B combine, that is AB, they have the lower molecular interaction, they have the weaker molecular interaction as compared to AA and B. Okay? That means it would be easy for AB to escape. Moreover, since it would be easy to escape it, the vapor pressure of the component would increase. Okay, so the graph which we have represented like this, in which we have written x1 equals to 1, x2 equals to 0, x1 equals to 0, x2 equals to 1. This is my P1 node, and this is my P2 node, which is slightly above than it. This was representing like this, we have done in our yesterday's class. But since they are showing the positive deviation, that means all components are showing this one as the XI. Okay. So the line which is completely represented, this is my the positive deviation, then the Rolle's law. Whereas the lines which are in the form of dash form, this is my ideal solution. And this is my non-ideal solution because it is showing positive deviation. That's why we have created it like the positive. Okay, we have shown it that it is representing a greater effect than the normal ideal solution. Clear? And we have also come to know that the components have much greater interaction between itself rather than the another component. Clear? Let's take a simple example that would clarify your concept also. Okay, we have the example of ethanol and acetone. Okay, ethanol and acetone. Now let's see in this compound, the ethanol is C2H5OH. And we know very well that most of the organic compound contains the hydrogen bonding in them. Clear? Now we have told that AA and BB interaction is greater. That means C2H5OH, a molecule of C2H5OH with another molecule is very strong, or we can say very stable, due to hydrogen bonding. But if we add acetone into it, the acetone would enter into this bonding and weaken this bonding. That means the space between the two ethanol molecule, the acetone would try to enter into this so that it would start breaking down the hydrogen bond. Am I clear? When it starts breaking down the hydrogen bonding, now the concept which has been formed, the ethanol acetone molecule, this is now weaker. This has the weaker bonding as compared to the previous. Clear? Now it has the weaker bonding, so if we slightly increase the temperature, the vapor pressure would be high. It would be very easy for it to evaporate as compared to pure ethanol. Clear? So this is how we can say the compounds, these are showing the positive deviation. Same as it is, another example is ethanol, sorry, not ethanol, acetone and carbon disulfide, CS2. This is also showing the same interaction. Clear? Okay, now we have done the positive deviation. Same as it is, we're going to move to the compounds which are showing the negative deviation. As you have seen that in the positive deviation, we have checked out that AABB are much greater. यानी इनकी अपने साथ ही bonding ज़्यादा strong होती है as compared to another one. But when I'm saying the weaker interaction, now the concept would be just reversed. Okay, now the concept would be totally changed. Let's see how it is changed and what are the example of it. Okay, I'm just writing it by showing negative deviation. They are the same molecule, the same molecular interaction level, but now the AB interaction is stronger than AA and BB. If the AB interaction is stronger, if the component have become a solution, now it would has the strong intermolecular bonding. Would it be easy for us to escape? Would it be much volatile now? Definitely no. We have to provide more energy so that the bonding would be slightly loosened, so that the bonding would be weaker and we can evaporate. Okay, so the concept has totally changed because of the strong interaction between the AB. So it would be hard, or we can say difficult, for AB to escape. Moreover, the vapor pressure of component would decrease. Am I clear or not? So my non-ideal solution that was showing negative deviation, because the vapor pressure has been decreased. As the vapor pressure has decreased, the whole diagram would be changed and it would show the negative deviation. Okay, let's see how is it happening now. Okay, now the diagram would be totally changed, and since it is showing negative deviation, so the overall pressure, vapor pressure P, which is equals to P1 naught plus P2 naught, now it would be decreased like this. Okay. All right. So the complete line, the solid state line, this showing me the negative deviation, whereas the dotted line represent the vapor pressure of the ideal solution, which says that P1 plus P2 naught would be equal. Clear? This is known to be the non-ideal solution. Sorry, yes, non-ideal solution representing the negative deviation. Am I clear? Now let's take a simple example of this also. For example, we have taken the chloroform and the acetone. Okay, now let's see. Whenever we have taken the non-ideal solution, we have told that chloroform and acetone, they have been arranged in the form of strong interaction between the two. That means if I'm taking the interaction between the chloroform and the acetone, they have now weaker interaction between itself. But whenever we will combine the two topics with each other, or we can say the two molecules, two solvent into each other, what would happen? They would make a great hydrogen bonding now. Let's see how is it happening. This is my acetone. And chloroform is CHCl3, that is so this is known to be hydrogen bonding. Which was not present when the chloroform was not dissolved into acetone. Okay, now the bonding has become stronger. We need more energy to break it down, to escape it, to evaporate it. Ultimately, vapor pressure would be lower down, and our result would show the negative deviation. Okay, but this negative positive deviation, this is just told by the graphical method, nothing else. Okay. So this is done now. Let's see the another topic, that is the agiotropes. What are the agiotropes? Agiotrope is a very simple topic, very short topic. Agiotropes are those binary compounds which boil at a particular temperature. Okay, let's see what are the agiotropes and how can we identify them. What are their examples also? Let's check out. Okay. Agiotropes means we are taking the example of two binary compounds, or we can taking the two molecules which are dissolved into each other and they would boil at a constant temperature. Okay, let's see the example of agiotropes. These were given here. Okay, yeah, first point I would like to say, binary mixture, that means two components are dissolved, boil at same temperature. Moreover, they have the fixed composition, or we can say same number of molecules at vapor phase as well as the liquid phase. Okay. These are known to be agiotropes. Okay. Now agiotropes are also two types. First one is minimum boiling agiotrope and second one is maximum boiling agiotrope. The solution would show positive deviation. They would represent minimum boiling agiotrope. Whereas another example, if I'm showing the solution negative deviation, they would show maximum boiling agiotrope. Yeah, that's it. And you also have come to know why is it so? Because if they're showing positive deviation, their vapor pressure is already high. So we have to represent them only the very minimum temperature. That's why they're called to be minimum boiling agiotropes. Okay. On the other hand, if I'm saying the negative deviation, that means we have to provide them much temperature so that its temperature would maintain the boiling temperature and it would make the compound boil. It would make the vapor pressure at a temperature or at a level so that it would be easily evaporated. Clear? Now, this is the topic we have done about agiotropes, about non-ideal solution, ideal solution. We have non-ideal solution, Rolle's law, Henry's law, and agiotropes. Okay. So now let's move to the next topic that is very important, very crucial for your board exam, as well as we can say for your UT1 also. That is the chapter topic, collocating properties. Okay, so let's begin. What is the topic we are studying? The collocating properties. Clear? You have already heard about the topic. This particular topic, bache, the colligative property, if I'm talking about the board exam, it is very crucial because it would give the direct question, one as a numerical question and the another one as a derivation. You have remembered that my colligative properties are basically of 4 types, the boiling, the freezing, the osmosis, and the lowering of vapor pressure. Clear? So 4, you will get one numerical question definitely, and if you are lucky enough, you will get one derivation also on either of them. I'm not specifying any one of them. Either any one of them, you will get a derivation as well as numerical. Okay, otherwise numerical would come 110%. Clear? So the topic is very important. Let's begin. And please, bache, I have told you that in chemistry, we are studying right now physical chemistry. The first 5 chapters are of physical chemistry. And the solid state solution, electrochemistry, we will study for the kinetics and surface chemistry. All the 5 chapters, since made up of physical chemistry, the numerical portion is very important. Clear? In the last chapter, we have done a lot of numericals. In this chapter 2, if we will get time, we will try to solve the numericals. But the point is, focus, have a great focus on numerical portion also in these 5 chapters specifically. Okay, so let's start with the colligative properties, and hopefully we will complete the first colligative property, that is relative lowering of vapor pressure. Let's see. Okay, first of all, you know what is the colligative property? What is the definition of colligative properties? These are the properties which depend only on the number of molecules of the solute rather than the nature. This topic is totally different, or we can say totally opposite from the previous topic. In the previous topic, either we're talking about ideal or non-ideal solution, but we have understood that the nature is very important. On the basis of nature, we have checked out the bonding, and on the basis of bonding, we have understood which is negative, which is positive deviation. But these are which dependent only and only the number of molecules. Okay, so let's start the first property, that is the relative lowering of vapor pressure. Okay, lowering of vapor pressure, as the name says, we have to check out what is the concept behind the lowering of vapor pressure. That means if we have been given a pure solution or a pure solvent that contains a vapor pressure, but if we add a solute into it, its vapor pressure would be decreased. Am I clear or not? Vapor pressure of solvent containing solute would be less than vapor pressure of pure solvent. But this is very common because the solute which has been dissolved in the pure solvent, that is behaving as an impurity. Okay, पहले मेरे पास सिर्फ water था that was evaporating its rate. Now if I'm adding any kind of substance into it, it would we can say it would take more temperature, because first of all it would have to reduce the bonding between the two, and then it have to boil the pure solvent. Okay, so let's start. First of all, according to Rolle's law, we have heard that P1 equals to P1 naught X1. Yes, that is the component, that is the partial vapor pressure of one component, that is equals to the vapor pressure of that pure component with the mole fraction. Now, as we have told you that the vapor pressure of solvent containing the solute, that would be less than the vapor pressure of pure solvent. That means my another concept is we have been taken P1 naught minus P1, that is equals to delta P1. Am I clear or not? This delta P1 is known to be lowering of vapor pressure. Okay, now let's combine the two equations. what would we get? Delta P1 equals to P1 naught minus P1, as we have understood that P1 is equals to P1 of X1. We would take this one, and that's all. Okay. Moreover, X1 plus X2 equals to 1. So X2 equals to 1 minus X1. So delta P1 equals to P1 naught X2. Clear? Now let's move. Now, if we go on further, what would we get? Delta P1 over P1 naught is equals to X2. Okay. This is also going to be relative lowering. So this is equals to P1 naught minus P1 upon P1 naught equals to X. That's it. But this is not a complete formula, because in this we have to calculate the number of molecules, we can say. So we will change the equation with the help of number of molecules. We know very well that mole fraction is defined as number of molecules of the solute, or we can say number of molecules of that particular component divided by the total number of molecules that are present in that particular solution. Okay, so now my equation would be changed, and it would become it would become like this. P1 naught minus P1 upon P1 naught equals to N2 over N1 plus N2. Am I clear? Okay. Now the point is, we have taken the concept in N1 plus N2, the amount of N2 is as lower as compared to N1. That means N is lower than N2. So it has now become clear. Further, we would solve it by taking okay, and in this way we can easily calculate the mass. All right, let's see a numerical on it that would further elaborate the concept. The question is, we are given the vapor pressure of pure benzene at a certain temperature is 0.850 bar. That means pure benzene, that means P1 naught is given rather than P1. Okay, let's check. P1 naught is equals to 0.850 bar. Then we have been given a non-volatile, non-electrolyte solid weighing 0.5 gram. That means W2 is equals to 0.5 gram. Okay, one more point, bache, I have told you that we have taken in all the colligative properties the second as a solute. Okay, that means W2 M2 that represents the quantity of solute rather than the solvent. ये चीज याद रखना, otherwise the whole concept would be wrong. Okay, so the W2 is equals to 0.5 gram, and it is added to 39 gram of benzene. That means W1 equals to 39 gram of benzene. We have also been provided with the molar mass, that is equals to 78 gram. The vapor pressure of the solution, that is P1 equals to 0.845 bar. So P1 naught minus P1 upon P1 equals to W2 M2, W2 M1 upon W1 M2. Okay, we have to calculate the M2. All other properties have been given to us, so we can easily solve it by 0.85 minus 0.845 divided by 0.845 equals to what is W2? We can solve M2, and this complete equation has come equals to, okay, this is not given in the book. You can solve it very easily. This is almost equal to 0.05 divided by 0.845. That is Okay, so you can easily solve the question with the help of this equation. Same as it is, we have done our first colligative properties. We have been provided with other colligative properties too. That is relative. We have done the lowering in vapor pressure. Now we have to understand the other concept, that is elevation in boiling temperature, or depression in freezing point, and last one is osmosis. Okay. Among all these, the very short question I would like to say, either I'm talking about the UT one or your board exam, that would come from osmosis. Because in osmosis there are so many concepts: semi-permeable membrane, isotonic, or we can say hypotonic, hypertonic, reverse osmosis, and it has also derivation. The derivation are mostly important for the other three, but osmosis is important for your MCQ question. So do not leave this concept. Okay. Since we do not have much time left, we will take your doubt session. If there is any kind of doubt or query in this topic, please let me know, or any suggestion that what chapter we need to revise if we get further classes, more classes. Yes, class, any kind of doubt or query, please let me know.